Okay, let's go through a couple examples of combining means and variances. And this is part of the last video, so this is like part 2. So if you haven't watched part 1, go watch part 1. If you're here, good job. Okay, so it says a company markets 16-ounce glass bottles filled with honey. The mean amount of honey per bottle is 16 ounces with a standard deviation of 0.1 ounces. The mean weight of the glass bottles holding the honey is 5 ounces with a standard deviation of 0.5 ounces. All right, here we go. So I'm going to define my variables. I'm going to say H equals the weight of honey in a bottle and B is the weight of a glass bottle. Okay, so the H is literally just the honey floating out in space. How much does the honey weigh? And B is the glass bottle itself. So what is the mean weight of a filled bottle? A filled bottle. So that would be, I'm going to take the honey and I'm going to put it in the bottle. So that should be a combination. I'm going to use F for filled is H plus B. Okay, so means behave, so I should be able to just combine those means. So the mean of H plus B should be the mean of H, which is 16, plus the mean of B, which is 5, giving me 21 ounces. So remember that means that on average, a typical value of a filled bottle should be about 21 ounces. And we would expect some variation in that as well. Okay, what is the standard deviation of the weight of a filled bottle? All right, so I'm looking for the standard deviation of H plus B, but remember, because this is standard deviation, it's like a Pythagorean theorem problem. It's like a right triangle. I can't just take H plus B and get that filled. I can't take the standard deviation plus the standard deviation. Instead, I'm going to take the variances. The variances add. So to find the variance, it would be the standard deviation of X plus B squared, the variance, is equal to the standard deviation of H squared plus the standard deviation of B squared. So I'm going to take 0.1 squared plus 0.5 squared. That gives me 0.26. Okay, that's my variance. And then we'll take the square root to get the standard deviation. The square root of 0.26 gives me 0.51. And if you notice, that is not the same as adding those two standard deviations together, because that would give you 0.6 ounces, which is not the same. All right. So what if I said, suppose we sell 4 bottles in a case. What is the mean weight of the case? The mean weight of a case. So we're talking about a filled bottle plus a filled bottle plus a filled bottle plus a filled bottle. I'm going to take 4 filled bottles and I'm going to put them in the case. Now to do this, that would be the mean of F plus F plus F plus F, and means behave. So I could do 21 plus 21 plus 21 plus 21. In other words, 4 times 21. And excluding the box, of course, because we don't know how much the box weighs here, would be 84 ounces for those. Okay, so what about the standard deviation of the weight of a filled bottle? We know that is 0.51. So what if we sell 4 bottles in a case? What's the standard deviation of the case? All right, so we think, okay, I need the standard deviation of F plus F plus F plus F. Okay, so when I go to do that, that feels like 4 times the standard deviation of F, but it's actually not. Okay, so you have to be really, really careful. There is this weirdo thing that happens in statistics that we need to talk about. Okay, so before we answer this question about how to find the standard deviation of F plus F plus F plus F, why can't we just do, we did 4 times the mean, why can't we do 4 times the standard deviation? Multipliers affect standard deviation, right? We're going to go on a side quest. All right, so join me in my side quest here, Adventures in Standard Deviation. So in statistics, when we're talking about combining random variables, this is one time where algebra does not apply. In other words, when we're talking about a random variable x, x plus x plus x does not equal 3x. Or in our case, in the previous problem, x plus x plus x plus x does not equal 4x. Okay, and here's the reason why. Let's imagine that we have a spinner, and on the spinner there's 3 sections. There's a 1, a 2, and a 3. Now if I take 1 plus 2 plus 3 and divide by 3, I get a mean of 2, and if I was to find the standard deviation, I would get 0.816. That's the standard deviations of this set of 3 numbers, 1 plus 2 plus 3. Now, in theory, if I say x plus x plus x, what I'm basically saying is I'm going to spin 3 times, and I'm going to find the sum. So x, that's any of the results from the first spin, plus x, any of the results from the second spin, plus x, any of the results from the third spin. I'm going to add those together. So I'm going to spin 3 times and add them up. Now, if there's 3 ways to spin the first time and 3 ways to spin the second time and 3 ways to spin the third time, we're talking about a set of 27 values. And it's every combination. So 1 plus 1 plus 1, 1 plus 2 plus 1, 1 plus 3 plus 1, 1 plus 2 plus 2, etc. All the different ways that you could spin those 3 spinners. Okay, so if I think about this in terms of those 27 values, this is what this would look like. The very smallest number you could get would be 3. There's only one way to get 3, 1 plus 1 plus 1. The very largest number you could get would be 9. That would be 3 plus 3 plus 3. And then I went through and figured out what all those 27 combinations were. You're welcome. And here's what it would look like. Now, if you look at this, you can see that the mean looks like 6. This is symmetric, so the mean and median should be the same. And so here's what, that's pretty straightforward. Now, if I think about 3x, 3x is saying triple the value on the spinner. Take the x value and triple it. That means I've got 3 values, 3, 6, and 9. So x plus x plus x is like spin, 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 and add the spins. 3x is like saying triple the value on the spinner. There's only 3 things, so that'd be 3. So take your spinner value and triple it. 3, 6, and 9 would be those 3 values. So if we think about it in terms of still having 27 values, okay, if I was to take that in 27 values, they would be equally distributed amongst the 3, the 6, and the 9. Okay, there's only 3 results. I can't get a 4, and I can't get a 5, or a 7, or an 8. So it still looks like the mean is 6, but the standard deviation of this guy down here that's in red, this is a larger standard deviation than up here. On average, these numbers, there's a ton of numbers at 3 and 9, which are very different from the mean of 6. Whereas up here, you have several numbers that are close to the mean of 6. Okay, so we would expect that the standard deviation of this one down at the bottom, standard deviation of 3x, is not going to be the same as the standard deviation of x plus x plus x. Okay, this one looks like it's going to be larger due to that. So in terms of our value here, again, we've got our spinner. Got to figure out where to put my face. Put my face under side quest. There we go. All right, so here are my pictures, x plus x plus x and 3x. So if I'm talking about the mean, okay, x plus x plus x, okay, I can think that's the mean of 2 plus the mean of 2 plus the mean of 2. That gives me 6. You can see that looks like what the probability distribution would have a mean of. And if I think about 3x, this means behave, so 3 times 2, that's also going to give me 6. So even when we've got this interesting thing where x plus x plus x is not 3x, the means are still behaving just fine. All right, so let's bring on the standard deviation. Standard deviation of x plus x plus x, I'm going to have to combine the variances. Okay, so even though it's not like Pythagoras anymore because there's only 2 sides, I'm still going to add the variances, and then I'm going to take the square root to find the standard deviation. So it's the standard deviation of x squared plus the standard deviation of x squared plus the standard deviation of x squared, and I'm going to take the square root of that result to get standard deviation. So basically there's 3 standard deviation of x squareds. Okay. All right, and I plug my number in, and I end up with 1.41. If I go to do 3x, remember standard deviations are affected, so I'm going to do 3 times 0.816, and notice I get 2.418. So these are not quite the same. I don't get the same standard deviation. I do see that the red one does have a lot more variation in it than the black one does. All right, so back to the honey bottles then. Okay, if I'm talking about 4 bottles in a case, I want the standard deviation of f plus f plus f plus f. So I need to find the variance first. So I'm going to take the variance of f plus the variance of f plus the variance of f, or standard deviation squared, standard deviation squared, standard deviation squared. Okay, there's 4 of those for easy math here. So instead of being 4 times 0.51 quantity squared, there's just 4 of these 0.51 squareds. You could also do 0.51 squared, 0.51 squared, 0.51 squared, etc. So the variance would be 1.04, and then I would take the square root of that. Okay, so you just need to be really careful. All right, here's another one. Suppose the average SAT math score is 625 with a standard deviation of 90. The average SAT verbal score is 590 with a standard deviation of 100. The composite SAT score is determined by adding the math and verbal portions. What is the mean and standard deviation of the composite scores? All right, so math is a 625 with a standard deviation of 90. Verbal is a 590 with a standard deviation of 100. And we know composite is happening by adding your math and verbal scores together. All right, so to find the mean, my face is in the wrong place again. Here we go. To find the mean of the composite score would be the mean of the math plus the mean of the verbal, because means behave, giving us an average score of 1215. And then I run into a little bit of a problem. All right, so math and verbal scores are probably not independent. In fact, I know they're not independent because each math score is paired with a verbal score. This isn't, they don't, to give you your SAT score, they don't just randomly pick a math score out of a hat and then randomly pick a verbal score on the hat and combine them and give them to you. It's your math score and your verbal score. They are linked. Okay, so it's not like the spinner where you're spinning the spinner and then spinning it again. This is once you've taken the math, you also have your English score. These are paired data, and paired data are not independent. Here's another way to think about this. In our last chapter, we said that the probability were independent, the events were independent if it didn't change, right? So what's the probability of selecting someone and finding out they had a high verbal score? Okay, so if I think about that in terms of, and then I say, what if I know they have a high math score? Okay, if I know a person has a high math score, if I'm only looking at the people with the high math scores, what would be the chance of picking a person with a high verbal score out of that? And I think that it would probably be a better chance, a higher probability of getting someone with a high verbal score if you're also looking at the people who got high math scores than if you're talking about the chance of getting a high verbal score out of just anybody who took the test. Okay, so in this case, because those are not the same, we're also not talking about independence. So whether or not you think about it in sort of philosophically here, these are paired data are not independent, or you think about it in terms of probabilities, either way, these are not independent. So I'm not worried about my mean because means behave, but I know that I can only combine variances for independent variables, and these are not independent variables, which means I cannot find the standard deviation. It cannot be determined. If this is a multiple choice answer, I would look for cannot be determined, can't find it. What I don't want to do is just ignore the fact that the independence is an issue and just find it anyway. Okay, if they don't come right out and say independent, there has to be a good reason for you to believe that they are. If you don't believe that they're independent, then we can't use that standard deviation combination formula. All right, I have another example. Here, this one says 2 random variables x and y are independent. Yes. All right, that means I know I'm good with standard deviation. The means and standard deviations are given below. What are the values of the mean and the standard deviation of 2x plus y? All right, and they've got this weird kind of chart. So again, what this is saying here is that the mean of x is 6 and the mean of standard deviation of x is 0.5, mean of y is 8, standard deviation of y is 0.6. All right, so to find the mean of 2x plus y, remember means behave. I'm going to take 2 times the mean of x plus the mean of y, I end up with 20. All right, so we can get rid of a and b. We're left with these right here. And if I had to guess among the ones that are left, I would not pick 0.5 plus 0.6 equals 1.1. That looks like that might be something that would be an outlier to us. So let's see what else happens. So I know they're independent. So if I want to find the standard deviation, I need to first start by finding the variance. So remember, the variance would be the standard deviation of 2x. Plus the standard deviation of y, both of those squared. Since that's 2x, I'm going to do 2 times the standard deviation of x. Because it's different from x plus x, right? Different. All right, so 2x there. I'm going to multiply those. I end up with 1.36 as my variance. Square root that to get 1.17, which is answer choice E is our correct answer. And it looks like I didn't mark that there. All right, so what do I need to know? So first off, means and other measures of position. So any kind of measure of position, we're talking about the 25th quartile or the median, anything that tells you where something's at, the maximum, the minimum, mean. Measures of position behave. That means we're talking about linear transformations on random variables or combining 2 random variables. Whatever the mathematical effect on the mean is going to be the same as the mathematical effect on the values of the variable. So whatever you're doing to the variable, the mean behaves in kind. Now, standard deviation and other measures of spread do not behave. So you're going to have to memorize how to deal with standard deviations. First off, the linear transformations, that's when you're adding or subtracting or multiplying constants. Only the multipliers affect standard deviation, okay, because it's a spread. So when you double your data, your spread doubles, but when you add 9, it just scoots over. Okay, so ignore those plus C's and only deal with the multipliers. If I'm combining 2 random variables, they must be independent. Otherwise, you can't figure out what the standard deviation is. And also remember, variances always add. Even if it's x minus y, the variance will add, and you're going to solve by thinking Pythagorean theorem. Okay, so it's the standard deviation squared plus the standard deviation squared gives you the standard deviation squared. Okay, and that works even with like 3. If there's 3 of them, x plus x plus x, it's squared plus squared plus squared equals squared, and then find it, take the square root. Okay, and then finally, x plus x does not equal 2x in statistics. And I know that's super weird, but here's again is that idea. Let's say I have a barrel of apples, okay? If I pull 2 apples out of that barrel and I add them together and find that weight, that is not going to likely be the same as taking 1 apple and doubling it. Okay, so if I take any given apple, okay, 2x is like I'm going to take the weight of an apple and I'm going to double it. X plus x is like I'm going to take 2 different apples and weigh them. Okay, and if I take 2 different apples, even if they're very close, their weight added together is probably not going to be the same as just one of the apples doubled. So we have to be careful. So in statistics, this is a little bit different. With means, you shouldn't have a problem, but with standard deviations, you do need to be careful. All right, thanks so much.